Okay, so now let's continue our discussion. Um, Basically, the energy that the material, the elastic energy that gets released has to go somewhere and there are two components, which is one is the plastic deformation of the regions around the crack, not just right in the vicinity of the crack, but a little bit around the crack, and the surface energy. Now, as you can imagine, when we have plastic deformations, we need to dissipate more energy because this guy is present. So it means if a material can deform plastically, like metals, typically many metals, not all metals, like substantial plasticity in metals, then propagating cracks will become a more difficult job. So basically this is, and these are energy per unit area, basically. This is what prevents what suppresses the crack growth. Now, for a very brittle material, we don't have much plasticity, so G1C is going to be pretty much this component. For materials that deform very plastically significantly, then this GP will, the plastic P stands for P, will be the dominant factor. Now, Griffith theorem in fracture mechanics relates the two energies that I told you. If the crack grows by delta A, the elastic energy around these regions will be released. There will be some plastic deformations here, as well as the bonds that are broken here in this region. The Griffith theorem brings these two types of energies, the one that is released with one that is dissipated, together, and it gives us a very well-known equation in the realm of fracture mechanics that relates the critical stress is the same as GC, GF failure or GC critical, to not just the crack length, which by the way is again 1 over square root of A, just like before, but also the elastic energy in the material and also the critical energy release rate. Okay, so now if I combine this equation with the equation that we had on page 4, this equation. So if I, this guy, oops, sorry. If I combine this equation with this equation, almost, yeah. That gives me a relationship between sigma F or sigma C, which are the same, which is proportional to a square root of C here for a given crack length. And also from the equation that was on page 4, GF or GC is also proportional to K1. And this is, I have to fix that. This is K1C, okay? And so these are our golden rules. And so basically I can rewrite these equations, and I can say sigma C or sigma F is proportional to G1C to the power of 1 over 2, which is proportional to K1C. Okay, these are the basic equation that we derive for this simple analysis of fracture mechanics. With these things in mind, now we are ready with the understanding that hopefully you guys developed or you had and reinforced between these two. the stress that it requires to advance a crack, and the energy. This is energy per, the critical energy per unit area, which we call it critical energy release rate. Let me write it down here. So G of 1C is critical energy release rate, and here I is for mode 1 fracture. And obviously you can have mode 2, mode 3, and so on, and so forth. These are, I call them our golden rules. Where did it go? Okay, sorry. I call them our golden rules, but these are not, this is my designation for this course. And so with that, we can now go back and look at a single self-healing experiment. Although we're talking in the context of intrinsic self-healing, this experiment that I'm explaining to you applies to both intrinsic and extrinsic. And everything I told you in this PDF document, in this handwritten document about fracture mechanics is also applicable to intrinsic and extrinsic self-healing. So the experiment starts with something like this. We have a crack length in the material, and we have an initial crack in the material. And in this case, we measure K, let's say K1C or G1C. And actually, if you compare it with the original terminology that we had, this is virgin material. Let's say during this experiment, we break the two. So basically, crack goes all the way, and boom, this material is broken. So it went all the way. Now, we put everything back together and trigger the self-healing mechanism. And after we trigger the self-healing mechanism, which is this part of the experiment, then we go back and redo this experiment. Okay, so this initial crack stays there. We keep it open because we need that to measure fracture toughness. And let's say we measure the fracture toughness again. And this time, when we measure it, we call it K1C of healed or G1C of healed. And the properties for the damage was 0 because the thing had to split apart. So now we have the two things we need to calculate the self-healing efficiency and everything. So now with that in mind, I want to focus the rest of this discussion on intrinsic self-healing, which I will start in the subsequent video.